today we're going to take a look at some applications of these vectors. And so we've covered everything we're done today. We're just going to put some words with it. So this first thing here is if an object's initial position vector is A and moves at a constant velocity B, its position at times t. And this is just like what we talked about before with our vector form of a line. So to find where its position is at x, y, we start with our position vector plus t, and we call this our directional, which is also our velocity, like what way is it going there. So this first one here, we have a remote control car. It's at initial of point -3,2 and moves with a constant velocity. So the first thing it asks us to do is the position of it, write the position vector of a car at any time. So to find its xy position, we start with its initial position, and we add, depending upon how many seconds have passed, its velocity vector of 2, 4, over 2 and up 4. So letter B says the position of the car at 2.5. So what is our xy position when it starts at -3, -2, and we want to know after, maybe it's 2.5 seconds there. Okay, so our x coordinate, -3 plus 2.5 times 2, and our y coordinate, -2 plus 2.5 times 4. Well, let's see, 2.5 times 2 is 5, plus -3 is 2, and our y, 2.5 times 4, 9 minus 2 is 6. So it would be at the coordinates 2 and 6. Wait, something seems wrong there. What's 2.5 times 4? That didn't seem right. 10. Sorry. Yep, double 8, 9, 10, so minus 2, so that would be at 8. Sorry about that. I was thinking something doesn't seem right. So it's at the coordinate. The position is at 2, 8. Letter C says the time when the car is due north of the observation point. The observation point, we're missing part of the problem there, is the origin. So we want to know that time when that car is at 0, 0. So we want to know, letter C, when is it north of the origin? So we don't know our y value, but we know our x is 0. So we have x, whoops, what was it? -3, 2. Plus t times 2, 4. So we don't know, we have two variables on the bottom, but we could find out when does 0 equal -3 plus 2 times t plus 3. So 3 equals 2t. So at t equals 3 over 2, or I would probably say 1.5 seconds. Now the next thing it says is plot the cars at t equals 0, 1/2, 1, 1.5, and 2. So let's see. So t equals 0. And we have our equation here. So we have the equation xy equals -3, 2 plus t times 2, 4. And we have to go 0 all the way up to 2. So t equals 1/2, 1, 1.5, and 2. Well, let's see, t equals 0. We know that's at -3, 2, because that's our starting. So 1, 2, 3, 1, 2. Well, we could easily figure out the 1, because what do we do? After 1 second, we go over 2 and up 4, 2, 3, 4. So this is like saying x equals -3 plus 2 times 1. Y equals 2 plus 4 times 1. So we end up with the coordinate -1, 2. 2 is also another easy one, so x equals -3 plus 2 times 2. Y equals 2 plus 4 times 2. Excuse me, that's a -2 there. All right, so what do we have? -3 plus 4 is 1. -2 plus 8 is 5. 6, excuse me. So let's see if this makes sense. We go over 2, so we're at 1. 1, 2, 3, 4. And we're at 5. So that makes sense that it's at 1, 5. And then we could do the same thing for t equals 1/2. X is -3 plus 2 times 1/2. So our x value would be at -2. And our y value would be at 2 plus 4 times 1/2, -2. So that would be at 0. And that makes sense because we're going over half this distance. So we go over 1 and up 2. So this one we go over 1 and up 2. And we should be at 0 and 4 because t is 1/2. So -3 plus 2 times 1/2. So -3 plus, whoops, and we're at 0. And then our y value equals 2 plus 4 times 1/2. So -2 plus 4 times 1/2. And we end up at 4. All right, the next one we're going to take a look at here is the position of a boat after it leaves the harbor is t equals 30, 15. A second boat is passing the harbor and its position is given by this equation. How far apart are there two boats at the time the first boat leaves the harbor? Well, when it leaves the harbor, what does that mean? It means our time is equal to 0. So when time is equal to 0, this one's leaving the harbor. So boat A, whoops, let's see if we can go forward here. So boat A is R equals T 30 and 15, and boat B is 55 plus T times 10, 10. So when R equals 0, this one's at the harbor, so its location is at 0, 0. When this one leaves the harbor, its location is at 50 and 5 because it hasn't gone anywhere. So how far apart are they? Well, the vector AB would be 0 to 50 is 50, 0 to 5 is 5, and that distance, so whatever the distance of the square root of 50 squared plus 5 squared. How fast is each boat traveling? Well, that is our velocity vector right here. So boat A, its velocity vector is 30, 15. So it's going over 30 and up 15. Well, how do we find how fast it is? What's that magnitude? So 30 squared plus 15 squared. All right, in the second one, boat B, its velocity vector is 10 and 10. So it is the square root of 10 squared plus 10 squared. Letter C. Are the boats in danger of colliding? Well, let's check out what is our x coordinate and our y coordinate. Well, our x would just be 30t equals 50 plus 10t, and our y would be 15t equals 5 plus 10t. Well, if we just solved one of these, let's see, when does 30t equal 50 plus 10t minus 10t? So t equals 5 over 2, 2.5 seconds, is when their x-coordinate would be the same. Is that the same for their y value? 5 plus 10t, 5t equals 5, so at t equals 1, their y coordinate is the same, so no, they're not at danger of colliding.